Jai Hind everyone. Welcome to the next second lecture of this theory of automata and formal languages. In this lecture, we are going to discuss the Chomsky hierarchy. Okay, so if we are going to talk about the Chomsky hierarchy, the Chomsky was a mathematician and he just classified the grammar, the computational grammar into 4 parts. So the first part was, he just gave that first part name type 0. So this part was partially computable. So all the problems or all the strings which are partially computable, they come into this part. So whenever we are talking about the grammar for this part or the partially computable grammar, so there is a term unrestricted you can see here. So whenever we are creating grammar for this type of languages, then there is actually no restriction, and we'll talk about what do we mean by the restrictions. And these grammars, they are recognized by Turing machines. Now this DTM, that is for deterministic Turing machine, and this NTM is non-deterministic Turing machine. So if we are having deterministic Turing machine or non-deterministic Turing machine, but with the help of that, we can just recognize a particular partially computable grammar. Now when we talk about the partially computable grammar, in the literature there are 2 more names for that. The one is recursively enumerable grammar and the another is phase structured grammar. The second part was context sensitive. So again there is a question that what context is. So we'll talk about when we talk about this type 1 grammar in detail. So in this grammar, the languages and the grammar both are context sensitive. So there are linear bound automata which are used to recognize such kind of languages or such kind of grammars. Now the third type is context free. So there are context free languages, and for that we are having context free grammar, and they are recognized by non-deterministic push down automata. And the last type is the type 3. So the language recognized by this type 3 are known as the regular languages, and the grammars which are available are right regular grammar or left regular grammar. And the DFA and NFA, they both are used to recognize such type of languages or such type of grammar. So by the hierarchy we can see that this type 3 grammar is a subset of type 2 grammar, and this type 2 grammar is a subset of type 1 grammar, and type 1 grammar is a subset of type 0 grammar. So we can say that if we are having a type 3 grammar, then it is also a type 2 grammar, it is also a type 1 grammar, and as well as it is also a type 0 grammar. But reverse we cannot say that. So it is not possible vice versa. So this structure is showing, this diagram is showing how we can just put together all those grammars or all those languages. So you can see that regular languages, so they are the subset of each and every other language. Now context free languages, so by this diagram we can see that if we are talking about regular languages, they are automatically are context free languages. Now similarly, they are computable languages, or basically we are just talking about the context sensitive languages. So if we are talking about context free language, it is automatically the computable language, or if we are talking about regular language, it is also automatically a computable language. Then we are having the partially computable languages. Now when we talk about the partially computable languages, these are the languages which are created by the unrestricted grammar. Then so we are going to discuss the type 3 grammar, and we are going to discuss all the grammars briefly one by one. So when we talk about the type 3 grammar basically generates the regular expressions. And when we talk about the type 3 grammar, in the type 3 grammar, if we are creating a production rule, then in that production rule we must have a single non-terminal on the left hand side, and on the right hand side there may be a single terminal or single non-terminal or a combination of one terminal and one non-terminal. So we can see that the production rules are of this form. So the production rule can be of this form, where we are having one non-terminal on the left hand side and one terminal symbol on the right hand side, or the rule can be of this form: x produces ay. Okay, so in this rule, one terminal is on the left hand side and the combination of one terminal and one non-terminal is on the right hand side. So here x and y, they are non-terminals, small a is the terminal, and the rule as is equals to epsilon. Now this rule is used to eliminate, or we can say the drop this symbol. So if you just want to drop this as symbol, we can just use this rule. So this rule is also allowed in this, but there is only one condition. That condition is S does not appear on the right hand side of any rule. So if S does not appear on the right hand side of any rule, then we can use this rule here. So these are certain examples of the productions of type 3 grammar. Now type 2 grammar. Now when we talk about the type 2 grammar, the type 2 grammar generates context free languages. Now in this, the production is in the form of A produces gamma. Now this gamma, this A is what? A is a non-terminal symbol, and this gamma, it belongs to the closure of union of terminal symbols or non-terminal symbols. So suppose we are having certain non-terminal symbols. Let's say we are having small a and small b. They are two terminal symbols, and we are having non-terminal symbols. Let's say a and b. So if I am writing a rule, A produces small a, B small b. So this type of rule, it can be possible in the type 2 grammar, but it is not possible in the type 3 grammar. So type 2 grammar is a little bit more free from these restrictions than type 3 grammar. And the languages generated by this grammar are just recognized by a non-deterministic push-down automata. So these are the examples of type 2 grammar, the production rules for the type 2 grammar. So such kind of production rules we can have in type 2 grammar. Now although you can see that these first 3 rules, they are also possible in type 3 grammar. So for regular grammars we can also use these kind of rules, but this rule is not possible in regular grammar. Although this rule is also possible in regular grammar, but this rule is not possible in the regular grammar, or we can say type 3 grammar. Now when we talk about the type 1 grammar, type 1 grammar generate context sensitive languages. Now the productions in this type 1 grammar are in the form of alpha A beta produces alpha gamma beta. Now where this A belongs to N, so we can say that this A is a non-terminal symbol. Now this alpha beta gamma, this belongs to, again this is a string of terminals and non-terminals, so it belongs to the closure of union of terminal symbols and non-terminal symbols. So we are talking about these 3, they are the strings of terminals and non-terminals. Now the string alpha and beta, they may be empty. So suppose if I am using alpha and this alpha is empty and this beta is also empty, then the rule will be in the form of A tends to alpha gamma beta. So you can see that this will reflect the rule for context free grammar. So if we are not having any context, then it will become a context free grammar, but this type 1 grammar is a superset for type 2 grammar, so that will also be possible in this type 1 grammar. Now this gamma must not be empty, so we can just not reduce this A. So there should be something, the gamma should be certain string of this terminal and non-terminal, and at the same time we can use this null production rule, and again it is allowed if S does not appear on the right side of any rule. Now the type 1 grammar, again we are having certain examples for the production rules of type 1 grammar. Now the language which is generated by this kind of grammar is recognized by linear bounded automata. So you can see here that in the right hand side, again we are having certain string of non-terminals, and in left hand side we are having certain string of non-terminals, and in the right hand side we are having a string of non-terminals and terminals. So similarly you can see in the second production rule and the third production rule, this will be the same production rule we have discussed for regular grammar. So here if you are just taking a look at this particular rule, so we are replacing this B by this string, that small b, capital B and small c. So this A will remain intact. So we can say for this AB, A is left context of B. Now the type 0 grammar. So type 0 grammar, it is unrestricted, so we are not having any restrictions. So they are also known as face structured grammar, including all formal grammars, and type 0 grammar generates recursively enumerable languages. Now, when we talk about the recognizability or recognition of this kind of grammar, or the language generated by this kind of grammar, so the language which is generated by this grammar, type 0 grammar, is recognized by Turing machines. So the productions, we can have the productions of this form: alpha derives or alpha produces beta, where alpha is a string of terminals and non-terminals with at least one non-terminal. So there must be at least one non-terminal in this alpha. So if we are not having any non-terminals, non-terminals generally behaves like a variable. So if we are not having variable, what we are going to replace with? And this alpha cannot be null, and beta, it is a string of terminals and non-terminals. So these are certain examples for the production rules of type 0. So you can see that these rules are little bit similar of the type 1, as it is a superset of every other classification. So now these languages, they can be just categorized into two general parts. The first one is computable language, or you can say the decidable language, and the partially computable language. Now the computable language, the languages, they are generated by the first type 3 grammar, type 2 grammar, or type 1 grammar. But when we talk about the partially computable languages, they are just generated by type 0 grammar. So when we talk about the computable languages, so they are called decidable languages also, because the Turing machine can decide membership in those languages. Now it can either accept a string, or it can either reject a string. So that means we are able to decide whether a particular string is a member of certain language which is generated by a certain grammar. We generally call them decidable language. But in partially computable languages, most of the time we are able to recognize because of the Turing machine, but Turing machine cannot decide whether a particular string will be acceptable or particular string will not be acceptable. So for that, they are called partially computable. So that is why they are also, the languages are also called recursively enumerable languages. So the computable languages are also partially computable language. So if certain language is a computable, then we can also say that this particular language is also a partially computable. So we are going to discuss the proof for this. So suppose L is computable, then there will be a Turing machine M that decide membership in L. Now meaning of membership is that M accept on X if X is in L. So suppose X is a certain string, so M accept is in this X if X belongs to L. So L is the language for that. L is this computable language. Now if M rejects X, so it is possible only if X is not in L. So this is what decidability, whether in this case we are deciding the membership of a particular string in a Turing machine. Now we are just changing this M to M dash. So we are just finding out the transposition of this machine. So how we are going to do that? So for all combination QA for which the machine rejects at the transition, del QA is equals to QAS. So the new machine M dash, this will accept on X if X is available in L, but it will just loops on X if X is not in L. So that means we are not generating any result for rejection. So this is what? This is the partially computable part. So we can say that M dash recognizes L, but it do not give certainty about the acceptability, or we can say more specifically decidability of this X in L. So that's it in this video. In the next video we will discuss the regular grammars. So thank you.